now?
Yeah, now it's clear.
Okay.
Okay, then we can get started. So, good morning, everyone. We are happy to connect ourselves again and hope you all are safe and doing well. So, today we have our speaker, Supriya Mandal. He is a research scholar in the Nanoelectronics lab in TIFR. His research work primarily focuses on studying various magnetic systems, superconducting resonators, and some graphene devices. Supriya finished his bachelor's in physics from Scottish Church College, Kolkata. Then he joined TIFR in the Department of Condensed Matter Physics as an integrated PhD student. And I would like to say, apart from his academics, he also likes sketching, singing, and you are encouraged to find him on Instagram to see his beautiful illustrations. So, now let's come to today's topic for which Supriya is here. So, we all know about phonons, which are lattice vibrational modes in crystal. So today Supriya is going to tell us about something new called magnons, which are relevant excitations in magnetic system. So without further delay, let's welcome our speaker. And Supriya, it's over to you now. And one last point, we will follow our usual norm for taking the questions. So if you have any question, you may raise your hand or type in the chat box and we will unmute you. And also, Supriya, you are okay with questions during the presentation, right?
Yes, sure. Anytime.
Okay. Okay, then let's welcome our speaker. Supriya, it's over to you now.
Okay. Thank you very much, Joydeep, for this kind introduction. So this is the topic that I would discuss briefly today. Magnonics in two sublattice antiferromagnet. So just to begin with, let me first discuss what are magnons. I'm somehow not being able to change the slide. Let me just. Okay, fine. Okay, so magnonics, this field deals with what are called magnons, and magnons, just like photons, are quantum of, let's say, electromagnetic waves. Magnons are quantum of collective spin oscillations.
Supriya, just one small point. So
Yeah,
can you
sure.
please come a bit closer? Means the sound is a bit low, so people are having a problem to listen.
Oh, okay. Is it
Yeah,
better now?
now it's better. Yeah, now it's better. Yeah.
Okay, fine. Okay.
Yeah, great.
So just to before going into magnon, let me just explain how you can realize a spin oscillation. So to study the dynamics of any kind of spin, or you can think of it as a, like, if you think in terms of classical physics, you can think of a macro spin. And if you want to know its dynamics in the presence of a magnetic field, you have to write down the Landau-Lifshitz-Gilbert equation. So if you look at this picture on the side, so if you have a magnetic moment M, and there is a magnetic field H which is applied in that place, then what will happen is two different torque terms will act on it. So one will be this minus M cross H effective term, which is, you can understand that this is in a direction which makes this basically, this is one term and this is another term. So you can understand that one term makes it uh, precise around the magnetic field, and another term causes a kind of damping in the system. So what will happen is this magnetic moment, it will spiral down and try to align towards the magnetic field. So if the damping term was not there, which is called this Gilbert damping, then what would happen is this magnetic moment would have continued its precision, but because of this damping there is kind of a loss mechanism which drains energy out of the system, and eventually the magnetic moment will try to be aligned with the magnetic field. Now if there is some way you can provide energy to the system to sustain its oscillation or the precision, then uh, that will be oscillation, will be a continuous oscillation in the system. So that additional energy that is actually supplied using an electromagnetic field, that I will come in more detail in the next slides. But once you have understood the precision of a single magnetic moment, let's go to what will happen if instead of a single moment you have a lattice of moments, or like in any normal magnetic solids you have these lattice points which contain these spins or magnetic moments. And if you consider a system like this, then the Hamiltonian looks something like this. So this is easy to understand. If you look at the first term, this is the Zeeman kind of term. It's basically m dot h kind of term. So each magnetic moments are basically affected by the magnetic field, and this second term considers the exchange interaction between the neighboring spins. So this J, depending upon whether it is positive or negative, the system will show ferromagnetic or antiferromagnetic behavior. Now this Hamiltonian has been written in the direct lattice space, and if you use Fourier transform to convert it back to, let's say, K space, then you can write down in terms of these normal modes, h bar omega k and dagger ck. These are the raising and lowering operator for the magnons. So let me not just go into details, but explain physically what it means. So it means that if you go from a normal direct lattice space to the inverse space, you can think about modes of, or rather let's say you can realize oscillations of with different k vector. For example, if you take a simple example of a cubic lattice, then that h bar omega k has this expression something like this. Here again, the second term is the Zeeman term, and you can understand that irrespective of whatever the k is, it's same throughout. So this term which has the k, which is coming from the exchange term, because you can see this j term sitting there, that is really the term which lifts the degeneracy, and depending upon the k vector, or basically its magnitude, you will get, you will realize that the omega k will vary from this generic value depending upon the value of k. Now this is the full expression for a simple cubic lattice, but obviously for other systems it can become more complicated, and you can have other sorts of complications inside the system. Now, one special case of this situation is what are called magnetostatic limit. When your Ka0, this term is much less than 1, K is very small, which means that the wavelength is very large, or let's say comparable to your size of the sample which one is looking at. What will happen is this term will be almost negligible, and only this other term will survive. And that those are called the that is called the magnetostatic limit. Now these also, depending upon the sample geometry and other factors, these can have different sort of uh, like different sort of modes can be there which are in the magnetostatic limit. For example, if you have a spherical sample, then you can see these are the two magnetostatic modes in that system. There can be others also. So you can, if you look closely, that in the first panel you see all the
Sorry to
spins
interrupt,
are aligned in same
Supriya.
direction.
Can
Yeah,
you be a
sure, sure.
little
Yeah.
louder? I mean, it's not loud enough. Maybe
Is it
you
better
can
now?
use. Are you using your headphone?
I am using
Okay,
headphone,
maybe
but
if you
I
don't
don't know
use
why.
that, that will help.
Let me just 1 second test the microphone. Is it better now?
Let's continue for some time in this mode. The sound is better, but some background is coming. But yeah, let's continue for background.
Okay, let's try to see
Yeah,
what
yeah.
happens in
Let's
this one.
continue. Yeah.
Okay. So yeah, so that is the magnetostatic limit. And for example, if you have a spherical sample, then you can have these kind of modes, as I said. In the first one, if you look at it, all the spins are aligned in the same direction. It basically means all the spins are precision, like having precision in phase. So there is no phase lag between the spins, and this is generally called the Kittel mode. And if you go to higher modes, then you can have these kind of modes where you can see that there is no net magnetization. Unlike this mode, you can think about this mode that there is a macro spin which is precessing, taking into account all the spins together. But if here you can find that the net m is actually 0, but still there is a mode that is being excited here, and obviously the k is almost 0. Now there can be other situation where this k is non-zero, and you can realize what are called spin waves. Now what happens in these kind of systems, for example, if you consider a linear chain of spins, then there can be relative phase lag between different spins. And due to that, you can realize these different modes. So if you look at the tip of the arrows here, and if you connect, you can, so basically what you are doing is you are looking at the relative phase with respect to each other. You can realize that this has a one wavelength inside it, this has a half wavelength inside it. So these kind of different modes you can realize. Now
There
I'll
is
go
a
into
question,
detail.
Supriyoda.
Yeah. Okay.
So Suman asks that could you tell about physical significance of dissipative term in the Landau-Lipschitz equation?
Okay, so basically what happens is, so this is called a Gilbert damping term, and that Gilbert damping term, it is actually still a topic of research, because some aspects of it is phenomenological. So when there is a magnetic lattice, then there are coupling between different things. For example, there can be coupling between the magnetic structure and, let's say, the lattice structure. Through that coupling, what can happen is, if you excite a magnetization dynamics, that can get coupled to the phonon dynamics, and it can leak some energy through that channel. So these kind of, now this is just one example, but there can be other things which can get coupled to it. For example, in conducting systems, the conduction electrons, that energy can go to conduction electrons actually. So all these terms, they actually was phenomenologically included inside the equation as a Gilbert damping term, but it can have contribution from different aspects of the physics. Okay,
Okay, I
so
think the question is answered.
does that answer the question?
I have asked Suman to unmute. So is it answered, Suman?
Okay. Yep.
Okay, okay.
Okay, great.
Okay, so next let's move toward until now what I talked about are like about generic, like let's say a ferromagnet is there. So if there is a ferromagnet, all the spins are like similar, all the lattice point have similar spins. So the thing is easy to understand. Now let's move to what happens in case of antiferromagnets. And in antiferromagnets, as you know, the simple picture that one talks about is like adjacent spins have the same magnitude, but they are oriented oppositely. Now among them, one spin special topic I will talk about are which are called two sublattice antiferromagnets. Now I'll describe them, but these systems are interesting because first of all they have no net magnetic moment, but still you can excite different kind of magnetization oscillations inside that material. And side by side, because there is no net magnetic moment, you can easily understand that it will have less stray field due to the presence of a magnetic moment. And also if there is some other magnetic moments or materials sitting outside which is giving out some stray field, then this system will also get affected relatively lesser compared to if the system had a net magnetic moment. Now let's come to this two sublattice magnetic system, antiferromagnet system. And the typical example which I will give of is CrCl3, which is a material which has gained renewed interest very recently. So CrCl3 has is a van der Waals type lattice basically. So what that means is its full lattice is comprises of different atomic layers. So each atomic layer has the similar kind of lattice structure as graphene, which is this honeycomb kind of lattice structure in a plane. And if you look at alternating layers, the magnetization or the spins are basically aligned opposite to each other. So in that way, if you consider one layer to have a net magnetic moment which is ma, which is oriented rightward, then the next one will have it oriented leftward. Now that's why you can basically look at this system as these we are calling two sublattice, and you can uh, really describe the system from like very basic viewpoint as two spins together which are normally oriented opposite to each other, but there can be more complex scenarios which I will describe. Now the way to understand what kind of modes you can excite in these systems is to write down again the LLG equation for all these spins together, and taking into account their exchange field and the magnetization, all those things. And if you solve those equations, they give these simple solutions when the magnetic field is in plane. And what happens is if you plot these two modes with respect to the magnetic field, you will get these kind of simple modes. So you can see one of the modes has a linear nature, and another one has a nature which is parabolic. Another interesting feature is one of the modes has the frequency starting very low when the magnetic field is zero. Another one has a finite frequency when the magnetic field is zero. Now, this has an immediate similarity with phonons in solid, right? So, like remembering that similarity, one of the modes which has the frequency going towards zero when the field goes towards zero, that is called acoustic mode, and the other one is called optical mode. So in more details, what really is different between these two modes is in one mode, this MA and MB, they precess in the same sense. That is, let's say they are both precessing clockwise. And in other case, if one precesses clockwise, another will be anti-clockwise. So it's very similar to,
Supriya,
yeah,
yeah, sorry to interrupt. There
yeah,
is
yeah.
a question that can you please talk about more modes before talking about it? Can you talk about quantas? So Amit has asked this question. Amit, you can
Okay,
unmute and ask this more clearly.
Okay,
yeah, sure.
so the modes mean that the energy expression that you have written in the case space. So the different modes of these Hamiltonian, that are you talking about? So
Right,
yeah, yeah.
right.
So in order to have that, we should know, I guess, the mode of which thing you should talk about. So what are the quantas of the Hamiltonian, that I think if you clarify it, then it would be much better to us to understand.
Okay, so I guess you are asking like what kind of modes will be excited in this system? Is that your question?
Yes, yes. Actually, the modes and the
Okay, okay.
respective quantas. Yeah.
Yeah, so basically, if you have a mode, and like for example, let's say you if you consider a harmonic oscillator, then it has a spring constant and a corresponding frequency associated with it. Now if you like how much quanta you populate that system with, that tells you where your system is completely at. But if you are not going out of that mode, so you can think of these are magnetic quanta of that mode. So if I have a omega k, and k can vary, so I can realize different modes in the system, and for each mode you can talk about their quanta, and that you call the magnon attached to that mode. So that is the way of describing the things. So for example, if you consider there are these two modes that you can excite in this sublattice antiferromagnet, then you can talk about two AFMR modes. First of all, antiferromagnetic resonance modes. One is acoustic mode, another is optical mode. And correspondingly, when you are talking about one mode, you can talk about that magnon associated with that mode. Does that answer your question?
Yes, yes. It's very much clear now.
Okay, okay. So now the question is, okay, these two modes are there, but how will you really observe them? Or let's say, will you observe them together? Now that depends on symmetry arguments, whether you see these two modes together or not. But the way you can probe these systems is using a device which is like this. So it's basically shown in a U-shaped manner, but you can think of it as a straight line. It is called a transmission line. What it has is a central line, which is some kind of metal. Then you have two gaps, and then you have the huge, these two sides you can think of as a part of same metal, and it comprises the ground plane. So if you think in simple terms, this is just a waveguide. And if you are familiar with coaxial waveguides, for example a BNC cable, and if you imagine cutting it in cross section, and basically cutting it and opening it, then you will get something which looks like this. So there can be different geometries of waveguides. This is one of them. This is called a coplanar waveguide, and this is a transmission line formed out of it. Now what these are done is, these are basically, these helps in propagating RF signal through it. So one thing I forgot mentioning is this CRCL3, because of their typical exchange field associated with different layers, these show the antiferromagnetic resonance, which has the frequency in the gigahertz range. So that makes this transmission line kind of geometry an ideal way of exploring them. So what happens is, if you send RF signal through one of the ports, and it propagates through this channel and comes out of the other port. Now if you consider a current flowing through this line, you can imagine that the magnetic and electric field associated with that, and the magnetic field will have a direction which shown in yellow arrows here. So that will be very similar to your right hand rule of current flow in a wire. Now, if the CRCL3 is placed in this on top of this line, then what will happen is, whenever it undergoes a resonance condition in the application, in the presence of a magnetic field, it will draw energy from your channel to continue the precision overcoming the damping term which I talked about, and that will result in a dip in the transmission that will you will observe at that frequency. So that is really the way of probing these modes. So now let's talk about how the acoustic mode looks like first.
Hello,
So for
Supriya da?
getting the acoustic mode,
Hello. Yeah.
right? Yeah.
Can you go
Hello.
the that last slide?
Okay.
So here you have shown that optical AFMR mode. So
Mhm.
this mode is basically can be excited by optical source, light or something like that. This is why it is named like
No,
this.
no, no, no. Actually, it does not. No, actually, there is no As I said, like acoustic and optical, these are not like not terms which have been directly applied here. So these are some comparison or relative terms. So basically, if you, let's say, if you consider about lattice vibrations, then you can excite two kinds of modes in a let's say in a lattice in which there are the adjacent atoms are different, or there are two kinds of spin constant associated with that lattice. In those kind of lattice, you can excite two kinds of phonon vibration mode. One is called this acoustic mode, another is called optic mode. So what they mean is, in acoustic mode, both your atoms are moving together in the same direction. For example, either both of them are moving rightward, and next round they are both moving leftward. So they are both moving together. And in the optical mode, what happens is they move in opposite sense. That
Okay.
means if one atom moves rightward, in the
Okay.
same, at that same instant, the other one will move leftward, and vice versa.
Oh, thank you,
So
thank
yeah,
you.
yeah.
Yeah, I
It's
understand.
just a nomenclature basically here.
Yeah, yeah. And and
Okay.
and this HDC in the right side
Hmm.
bottom picture.
Hmm.
So this is applied magnetic field,
Right, right,
and you can rotate this magnetic field with respect to the sample.
right.
Okay.
So in our system, we basically rotate the sample instead, because this is a fixed
Okay.
direction,
Okay.
because it is
Yeah,
applied by
it
a
is.
solenoid.
Yeah. Sure,
Yeah,
sure.
yeah.
Thank you. Thank you.
Okay. So if you like, as I said, like exciting, which mode is getting excited, that will depend on the symmetry of the problem. So let me say in very simple term that this HDC, if it is, so if you consider the current here, the magnetic field is going around this central line, you can think about. So this HDC, that is perpendicular to the RF current. And if that is the case, that time the acoustic mode will be excited. So as you can see, this is the acoustic mode we see. So let me just describe what a color plot here means. The vertical axis is the frequency axis, the horizontal axis is the magnetic field axis, and the color here represents the transmission spectra from the system. So if you send some signal through here and observe the signal coming out of here, you compare their them basically, magnitude and phase both. And if you plot that magnitude, then roughly that is the thing which has been plotted here. Really, it is the derivative of that with respect to magnetic field for the data clarity. But let's not go into that detail. It's just think about it as the transmission spectra from this system. And you can see that there is a structure, that you can see a linear structure which I showed, which looks like the acoustic mode of the system. Now this is the acoustic mode of antiferromagnetic mode, but if you notice it closely, there is a point at which there is a knee kind of region, and from there the slope changes slightly. That knee region is nothing but the field at which the antiferromagnetic system is going a transition into ferromagnetic state. What that means is, if your magnetic field is high enough, then all the spins are getting aligned with the direction of the magnetic field, and the system is becoming really like a ferromagnet. And there are interesting things, if you can notice, like this has a, complex phase space with temperature and field. So if you increase the temperature, then these knee region comes down, and above certain point, what you basically, it is something like 17 Kelvin. What you observe is the electron spin resonance. That means the system is not really in any magnetic ordered state, but has become almost like, you can call, paramagnetic. Now this diagram, although it looks a bit complex, let me just briefly describe it, because it talks about some of the interesting features of the antiferromagnetic spin oscillations. So if you start with zero magnetic field, what happens is, to begin with, the system is in a canted state. What that means is, the two spins which I talked about, associated with the two sublattices, they are making an angle with respect to each other, which is but not really exactly oriented opposite to each other. You can say. Now this also happens after a certain. Sorry, I just misspoke here slightly. So no, to begin with, it is at its ground state, which you know that it is aligned opposite to each other. Now, if you start applying this magnetic field, remember that there is this magnetic field which we are called the DC magnetic field. That is only a part of the contribution that is affecting these pins. uh, Additional effects are dipolar fields, the exchange fields that are there, and also the crystal anisotropy. So anisotropy in any magnetic crystal is a plane or a particular direction in which the spins like to be aligned to. Now, if you consider all these magnetic moments together, because they are giving it a complex effective magnetic field, what will happen is if you really draw all the arrows together and consider how much one is affecting these spins, then you can see that these sublattice magnetic moments gets oriented in a direction so that they can't with respect to each other, as it is said, or makes an angle with respect to each other and also with the applied magnetic field. Now when that happens, so in this region what happens is if you apply a magnetic field, then both of the magnetic moments are like opposite to each other, so you cannot really realize exciting these two modes. But when they get into a orientation which has an angle with respect to the applied magnetic field, then these modes gets coupled to the field and these two modes can be excited depending upon the symmetry. And after this ferromagnetic transition, what happens is these two magnetic moments are aligned in the same direction, as I said, and it's almost like a ferromagnetic system. Now, as I said, this mode is realized when the magnetic field is perpendicular to the RF magnetic field. So as you can easily guess that the optical mode will be visible when the magnetic field is in the same direction or is aligned with the RF component of the magnetic field.
Yeah,
So if we do that,
sorry to interrupt. Can you
then
hear me?
yeah, sure,
Yeah, in
sure,
the
yeah.
previous slide, in this slide as well, in the 2D plot,
Hmm.
what does the color intensity signify? Like the blue and the red.
Yeah, so the color intensity signifies, yeah, okay. So you are asking that which is high, which is low, right?
Yeah.
Yeah, so this is transmission spectra, and blue is the low here and red is the high. But in this figure it will not make much sense thinking about that, because as I said, this is actually the derivative of the transmission spectra with respect to the magnetic field. So if you had plotted only the magnitude of the transmission, then you would notice that this feature here, that is in blue and the background is in red, so that represents an absorption. But in this case, because you have taken a derivative, then a Lorentzian, the derivative of a Lorentzian has this first up and then down, or first down then up, this kind of line shape. So here you can basically see blue by the side of red and there is a white region in between, so it's really like a derivative of a Lorentzian kind of shape. So this is done here because these signals are very feeble. Doing this derivative can make this signal clearer, in a sense that it will only accentuate the part which basically varies with the applied magnetic field. Does that answer your question?
Yeah, that answers my question.
Okay.
Thank you.
So there is another question by Gaurav.
Okay, sure.
So I will ask Gaurav to unmute. So Gaurav, you can ask your question.
So my question is, in the plot of this frequency versus HDC
Mhm.
line plot,
Right.
there something is there where MA and MB are slightly canted with respect to each other, no? So
You are
is
saying
no,
this
the
white line?
larger plot, the larger plot.
The larger plot, yeah.
Yeah, there is a small box where you have shown the two moments are canted with respect to each other.
Are you talking about this part?
No. The moments you have shown, MA and MB.
Okay.
Yeah, that one, the right way. So is this
Okay.
something like magnetic frustration?
Magnetic frustration. Okay, I don't know if it is directly linked with magnetic frustration. I don't know actually much detail about that system, but maybe that talks about system where uh, like if you like the very basic way I understand some of it is like if you have three spins, then if two spins are oriented in some particular way, then the third spin has different choices, and you can correct me if you know, right? It's something like that.
So I want to know why the system goes into that state.
So I think it's not magnetic frustration here.
Uh-huh.
What basically happens is if you have these different contributions, as I said, and another interesting part is now these two magnetic moments, because they are oriented oppositely. So
Mhm.
if you really think about contributions like like magnetic anisotropy or the relative exchange terms, those will affect these two spins in different ways. So the
Mhm.
angles are not same, and uh, the effect that these two spins faces, that will be slightly different. This is, I think, better to describe by drawing these contributions together. That will make it more clearer, but unfortunately I don't have it here. So that, then you can realize that these two moments will
Mhm.
actually not uh, orient in the same way. So what I mean is this full thing, if you consider this up and down spin to be a combined system, that will
Mhm.
not be fully affected, and as it will stay like this and rotate, let's say. That will not happen, but these individual spins will get affected differently and will make an angle in between them,
I
depending
see.
upon all the magnetic effects that are there. And notice that when you are going from this point to the ferromagnetic transition, these canting angle will vary until they ultimately gets aligned to each other.
Okay.
So it's really depends on the strength of the net magnetic field that changes this angle.
I see.
Yeah.
Okay, thank you.
So so if we now apply the magnetic field in a direction which is parallel or aligned with the RF field direction, because here if you notice the current is in this direction, so the field will be something like this. There we indeed see the optical mode, and again with increasing temperature, you can see that at some point of time this mode structure vanishes and gets replaced only by the electron spin resonance mode structure. But interestingly, we can see the acoustic mode also together. Now what can be the reason for seeing both the modes when we expect only one? So the reason is actually very simple. So our waveguide is a coplanar waveguide, as I said, and the magnetic field is, if you place your thumb along this RF current direction, then the magnetic field goes something like this. So it has different components. For example, on the central line, it is parallel to the plane of the CPW, whereas in the gaps, it is perpendicular. Now, because of that fact, what happens is in these case, so the field components which are there in the gap, they are actually perpendicular to the applied magnetic field, if you think it. And only in on top of the central line, the part is aligned with this magnetic field. So because of both these symmetries, here you can see both the modes. Now after that, so let us move to forward and introduce a magnon coupling between them. So until now the field was, let's say, in some particular direction that preserved some symmetry, and you could see only one mode. So that meant that the two modes are not coupled. That is also apparent from this crossing here. So the two modes are crossing each other at some point. So that tells that the two modes are not coupled and not affecting each other. Now, if you apply a magnetic field component which is perpendicular to this CPW plane, then that breaks this symmetry and basically introduces a coupling term which couples these two modes. Now, to deal with this kind of system is very generically speaking, if you have two modes which are the eigenmodes of a system, then these diagonal terms are zero. So to begin with, if the field was oriented in plane, then these two diagonal moments would have been zero. But now because it has this perpendicular component, you introduce these delta terms of diagonal terms that are non-zero, and that will mix the two modes. And to get the new eigenmodes, you have to solve this equation. And after solving this, you can get these new modes which are hybrid modes. So they are not acoustic or optical right now, but some hybrid of them. And you can see that these modes are dependent on both the angle of application of the field and the magnetic field itself. So if we plot these modes with different varying angles, they will look something like this. So the crossing will get replaced by a anti-crossing right now, which signifies the hybridization between them. So if you look at these figures, so 0 degree, 25 degree, 40 degree, and 55 degree, you can see that this anti-crossing is getting more and more prominent. So that signifies that there is a coupling between the two magnons. But along with that, another interesting feature, if you note, is with increasing of that angle. So to begin with, what were single modes, very clear single modes that are going through, now there are multiple of them coming up. Now, what can be the reason of them is, so what I briefly described initially. So there can be different modes. One is which are for k almost equals to 0, which are called magnetostatic modes, which which are more common to realize, and all the spins are precessing in phase there. So it's really a global kind of scenario. Those are the single modes which you were observing. Those are the acoustic and optical antiferromagnetic mode, and after the antiferromagnetic to ferromagnetic transition, that was the ferromagnetic mode. But now these additional modes are basically the modes which has non-zero k. So because this crystal has a thickness, and when you are changing the magnetic field component which is perpendicular to the plane of the CPW, this thickness of the mode, you can think of it is like a cavity, as you for example, in one dimensional whale or something, problems like that, what you have basically, there is some kind of oscillation. If you consider a string vibrating, there also it is the same case. So if there is some oscillation and you put two hard boundary conditions on both sides of that string, so standing waves will form in between them. So here also, if you consider the thickness of the sample to be making of that cavity, there are other effects that make this easier. For example, surface spinning and those kind of things. I'm not going into details. Then you can realize that these higher order k modes, they can now form so let's call them spin waves for now, not modes, because they are like not standing wave modes, because they will form standing wave modes only when there are boundary conditions available and they can really form a standing wave inside. So that is what's happening here. So when you are applying this magnetic field component which is perpendicular to the plane of the CPW, and because of there is a thickness, these different k's spin waves can set up standing waves inside this, and those are showing up as this additional modes there. So these are observed in the van der Waals antiferromagnet here, and just I am almost towards the end. Just before finishing, let me tell about like one application of this system, or let's say like probing it in slightly more detail, that what else you can do with these kind of systems is, for example, if I have a what you see here is a silicon wafer. On top of that, here is a, again, just for simplicity, think of it as a transmission line, but now you have closed one end of the transmission line, or here really actually it is open, which means that the central pin is not connected to the anything else in this side, and in this side there is a gap exists between your input feed and the transmission line. That what that does in very simple terms is it provides boundary conditions to the transmission line. Now as I said, any boundary conditions will help build in standing waves inside any kind of system which has oscillations inside it. So here, because those electromagnetic modes were like electromagnetic waves could propagate to the transmission line, putting boundary conditions here will set up photon mode inside this thing, and this is now a CPW resonator. Now these can have, once you are talking about standing waves, you can talk about like half wave, full wave, these kind of things depending upon what is the mode's pattern. And in this kind of pattern, there is a mode which has a current antinode in the center, which means that the RF magnetic field will have a maxima at the central part of it. So when we place a CRC crystal at that region, then what will happen is this magnons can get coupled to the photons inside this superconducting resonator. This this transmission line part is now made out of superconducting material to reduce the losses inside the system. So if you look at this diagram, this is just the transmission line data from the previous panel. And if you look at the right panel, this is the showing the uh, case where the photons and the magnons are getting coupled together. So this region is actually the region shown in gray dashed rectangle in the left panel. So what's happening is these two modes, they were the antiferromagnetic resonance modes here. They would have been something like these, but now because of the presence of this cavity mode, these magnons are getting coupled to the cavity. And again, just like when the two magnons coupled together, they showed up as avoided crossings. Here they are showing up as avoided crossings between the cavity and each of the antiferromagnetic modes. So in this region, you can think of these are partially photon, partially magnon hybrid modes. So one can realize more interesting things with this system, and use these to design or realize what are called hybrid quantum systems kind of scenarios, where you are basically coupling two different aspects of a system, and that can help in transferring information through different components of a system, as you can imagine. So that's basically what I had to talk uh, this about this antiferromagnets and the spin oscillations in between them. More details are available in these papers. So this is the these are the reference that are used for this talk. So thanks. Now you have any question you can ask.
I had a small question.
Right.
Yeah, you talked about magnon-magnon coupling
Yeah. Go
a
ahead.
few slides back.
Hmm.
Yeah, so is there a physical way of understanding this coupling? Because you mentioned the precession to be like clockwise, clockwise, and clockwise, anti-clockwise when we are talking about optical and acoustic modes independently. So what
Yeah.
would that translate into if we are talking of some coupling between those two modes?
Yeah. So right, that's a good question. So what? So when I was describing this picture, here there were some symmetry arguments that are there. So what happens is when you are writing down this full LLG equation, or in the so because you are really talking about very semi-classical picture in these cases, so you have not only the external magnetic field, but in the, so if you imagine the Landau-Lipschitz Gilbert equation. So there is this term which is H effective, and this H effective really takes into account like all the effects, your HDC which you are applying yourself, then the exchange field which is there due to, for example, if MA can affect MB and MB can affect back MA. So all these complex effects are there. So depending upon, and then there is additional like dipolar field, and then there is the magnetocrystalline anisotropy. All these effects are there. So when you write down and expand these equations, then you will see that there are terms which are which will be there in normal cases. For example, if you apply the magnetic field in any direction, then because of this particular system, you will see that this coupling term is actually present. This coupling term is actually present. But in this particular scenario where you are applying the magnetic field in some particular direction, that preserves some symmetry of the system, some rotational symmetry in the system, and that blocks the other mode from like getting excited or getting mixed with this mode. But when you break that symmetry, basically you break that symmetry by applying this perpendicular component of the magnetic field. So if you think about the components in plane, then they are not actually doing that job. So in plane component can only so if like very briefly describing, if these are two magnetic moments in your system, then they can either make them precise like this, or they can make them come closer and far away. This is just a very hand wavy kind of picture, you can like qualitative kind of picture, but you can get the essence of this. So when the field is in plane, then these can only affect the system in these two kinds of ways, and that's why it preserves the symmetry. But when you apply a component which is out of plane, then that breaks this symmetry, and there the case is general and the two magnons can get hybridized. So it's better to talk about that these are now my modes in the system, not about the two individual acoustic and optical modes.
Yeah, I think the
uh,
question is answered. So Shankar has a question. I will ask him to unmute.
yeah,
Yeah, hi. So I'm
yeah.
more interested to know about how you do the measurement actually. So how you uh, launch this radio, the gigahertz signal, and uh, what is the measurement technique? Like if you measure through lock-in,
Oh, okay,
or
okay.
how you apply magnetic field of say 100 millitesla, 400 millitesla, how you apply that. So these things. So if you don't
Okay, okay.
want to say here,
So,
I can contact you
yeah.
later. You can show me the setup. Otherwise, I'm interested for
Yeah,
this
yeah,
detail.
sure. We can discuss in detail, but for maybe just briefly telling. So, if, for example, just imagine this is a PCB, this is printed circuit board, and on top of that, you have this structure made, which is made out of copper in case of PCB, or in case of wafer, as I said in the case of the resonator.
Mhm.
It's some superconducting material deposited on top of a silicon wafer. So whatever it is a planar object, and you can load it in a rotatable sample holder, and you can have different launchers that you can connect with these ports. For example, here, because there is a central pin and there are these ground planes, there are planar launchers which are uh, so whatever cables and things we normally use, they are basically coaxial cables.
Mhm.
In this case, there are variants called SMA or SMP, but they are basically the
Oh.
details. So there are launchers which can convert that coaxial to a planar CPW wave kind of geometry. So if you attach one of those converters, basically two of those converters at these two ports, and then attach these two cables here, then you can use the instrument which is called a vector network analyzer, which can which lets you analyze any electrical circuit in full details, in the sense that if you send, so it is basically like, in a very basic way, it is a two it is to analyze two port systems, which means that it has two ports from which you will from one of the ports you send signal into your system, from another port you are getting the signal back from your system, and it lets you compare the reflected or transmitted signal from your system with the signal that you are sending into the system. So that comparison is both magnitude wise and phase wise. And if you have a
Okay.
two port system, then you can write down its response as a 2 by 2 matrix, which is called
Yeah.
a s parameter matrix.
Mhm.
And those different terms, like full magnitude and phase information, can tell you about how the system is reflecting the signal back, or how it is transmitting through. So that is used to send signal in and out of this system. And because we do these measurements at low temperature, these assembly is either if dilution fridge measurement, it is loaded in the dilution fridge inside a small sample loading chamber, or in, if we are using a wet cryostat to do the measurement, we are loading it in one of the insert sticks bottom portion, and uh, dip it inside the cryostat. The coaxial cables carry the signal in and out of the system. So we use this rigid coax lines that go into the system. So that is and the
Okay.
magnetic field is applied through a superconducting solenoid that is inside either the wet cryostat or the dilution fridge.
I
So
see.
that's why the direction of the magnetic field is always vertical. But
Mhm.
to realize this same situation, we tilt the sample plane accordingly.
Hello, Supriya.
The more, yeah,
Yeah. Oh, okay. Okay. You
yeah,
finish
yeah.
it. Uh-huh.
No, no, it is
So
fine. I was just saying
I
that we
have
can discuss in more detail. Yeah.
yeah, yeah. So I have a quick question. This is very nice and insightful talk. Thank you for that. And just I have a quick question. You talked about that quantum collective spin oscillation. So
Hmm.
can you
Uh,
tell a little brief that how you can correlate with your experiment? Just in yeah.
okay, so spin oscillations are basically so if you have a, let's say if you have a normal crystal lattice, then you like just giving a similarity with phonons and mechanical vibrations. So if you um, have a normal lattice and there are these atoms sitting at each point of the lattice. Now if you have a mechanical vibration in the system, then because there is mechanical coupling between all those lattice points, or the ions or atoms, whatever you call, so what will happen is they will, one atom will not vibrate itself, but it will affect the atoms neighboring to it also, and that effect can go on, and all the atoms can basically affect all other of them, and so there are different vibrational waves that are set up in the system. So if similarly, if you just think about a lattice, but now you are thinking not about the physical vibration, but what happens to, if it is a magnetic material, then those lattice, each of these lattice points, there are spins associated with those points. So now if you try to think about what happens if you just give a like some jerk or jolt to one of the spins, so it will do certain kind of motion. So in these kind of cases, that is realized by applying a magnetic field. And what these systems do, that you can, for example, in the other case from classical picture, you can apply, let's say, Newton's laws very simplistically, and try to look like what kind of coupling will be there and what kind of modes will be set up, how this one spin responses to whatever force you are giving to the system. But in case of magnetic material, it is really about the magnetic field and the torques that are applied on that magnetic moment. And here the corresponding dynamical equation is LLG equation, or Landau-Lipschitz-Gilbert equation. So if you write down that equation, then that will tell that okay, each of the spins will precess in certain way with respect to the effective magnetic field that it is seeing. Now, once it is doing some kind of motion or some kind of oscillation, then because these neighboring spins are attached or coupled by exchange interaction, one will affect the other, and that effect will again go on. And so different kind of collective spin oscillation means that kind of different kind of uh, net effect of magnetic oscillation will be realized in that system. And just like any of these things, you can write any general oscillation in terms of the eigen modes of that system. So it's basically similar to
Yeah,
the lattice vibration
yeah.
kind of picture, really.
But
Yeah.
in this case, you are applying DC magnetic field, right? And
Yeah.
if
So
in your lattice you have the specific orientation after applying magnetic field. Yeah,
in the lattice, right? Yeah.
yeah.
So
Then
here
how
what
the
happens is, hmm,
yeah, my question is
how the,
then how the I mean that
yeah,
wave of the spin has been generated here, means, with the DC magnetic field and specific
right, right,
orientation of.
right. That is a good question. Yeah. Yeah. So as I said, what happens is if you apply this, let me just go to the let's say this slide. So if you like imagine one of the spins, and it somehow sees some magnetic field and it starts precessing. But if there is no so that field which is about which it is precessing, that is the DC magnetic field, or that is not was oscillating is what I mean. So it will precess around the effective of that kind of field. Now if you just, there is no excitation in the system to provide your system any energy, then the damping will take over. And ideally what will happen is this, in semi classically speaking, this spin will precess and but also spiral down in a way and try to ultimately get aligned with the magnetic field. Now when it does that, there are these modes which are excited in the system, but they are, you can say, not long sustained. And if they are not long sustained, it's really the time scales in the system that tells you whether you can excite that mode or realize that mode or get the signature out of it or not. So you have to somehow make an arrangement so that you provide the system energy, but also provide it at the frequency at which it is performing those precisions, so that the damping it can overcome. And in that case, this precision can go on and on and on. Now when you are applying this RF magnetic field, remember that that RF magnetic field is uh, oscillating like this. So what that is doing is that is making these like, if you consider one of the atoms or one of the spins, then it is making that overcome that damping effect and continue its precision like this. And once one is processing all, it's basically similar situation for all of them, and they are coupled together, so all of these modes will be excited. And what will happen is, because your system will now continue precision by overcoming the damping at that particular frequency, which is the resonance frequency we talk about, you will see a deep in your transmitted energy spectra, because that energy which you have supplied into the system, uh, that has not come back to your output channel, because that has been taken up by the system and has gone out the leakage channel. So that is the
Okay.
significance of that, applying that RF magnetic field. Yeah.
Yeah. So for that meaning in simpler way, so your page is basically
Hmm.
something like you are mapping to some kind of wave. Huh?
Can you
Yeah.
tell me again?
So in your case, mean the phase that arises due to
Huh.
that spinning, you basically that phase difference you map to your some kind of wave.
Yeah, that is true. But one thing is, there need not be actually any relative phase difference between the different spins. So, for example, a Kittel mode is a mode in which all those spins, they are all precessing in sync. So, this is the very basic mode one can observe in a ferromagnet. So what happens is, so just because you have a coupling between all the spins and there is a precision of one of the spins, you can imagine that there can be boundary conditions or there is a possibility of exciting different kind of spin oscillations in the system. So the very simplistic of them is the Kittel mode, where you don't have any relative uh, phase difference between the adjacent spins. And that's why what you can do here is think of all these magnetic moments adding up and resulting in a single big macro spin, and as if that big macro spin is precessing around your applied magnetic field. So that is also precision, and that will also have the damping associated with it. And if you apply a magnetic oscillation at that, like near that resonance frequency, it will still take up that energy from your supplied RF in this case, and use it for overcoming that damping. But there is no phase difference between the adjacent spins. Whereas for spin waves which has this k not equals to 0, what will happen is they can have uh, phase difference between the adjacent spins. Now, one thing which is different from in this case from the Kittel mode or those magnetostatic kind of things is, now you can imagine if there are no boundary conditions, then these are basically propagating waves. So if you put no boundary conditions and excite one of the spins, then it will just be like a propagating wave. So that's why they have some speed associated with it, and it can basically carry information in that sense. But if you put boundary conditions, they can also reflect back and forth and make up the standing waves, but they will have some difference with respect to the magnetostatic limit.
Yeah, thank you. So if uh, host can give just allow me for one question, then I can ask one.
You can ask. Go ahead.
Uh,
Mm.
so in your experimental result, that color plot shows that basically no, next to, I think, yeah, that is, yeah, the spin oscillation, quantum collective spin oscillation.
Mm.
Yeah, so this just I could not understood properly. So if you just tell Miss Hort, quick, this what does this color
So
plot?
yeah, so when you, so the this colored plot, this plot of the color plot is clear to you, right? I mean, what has
Yeah,
been plotted,
mm,
or I can repeat again if you want.
just quick.
So okay, let me just briefly tell. So this vertical axis is frequency, the horizontal axis is the magnetic field, and what has
Mm,
been plotted is just the transmission through this transmission line. So if you are sending some signal to the input port of this, and you are getting some signal out of the output port, and you are plotting that transmission here.
mm,
Now what you are seeing is this different modes. Those are the portions in this diagram where energy from your supplied channel is getting absorbed by the system to perform some kind of spin oscillation. Now, if you apply a magnetic field component which is perpendicular to this CPW plane, then two things will happen. These, first of all, these two modes will get coupled. As I said, an avoided crossing will show up because now they are the hybrid modes. And along with that, another thing will happen is you will see this multiplicity of modes or these additional modes that are showing up. Now these are basically happening because this crystal has a thickness, and by applying a magnetic field which is perpendicular to the plane, you are basically using that these two boundaries of the crystal to make up essentially a one-dimensional cavity, let's say. So because of the surface spinning, the surfaces can give some hard boundary condition to these propagating spin waves, and when that happens, these propagating spin waves, which has this k not equals to 0, as I said in the beginning, those when propagating gets reflected from this surface, let's say, and reflects back, then again it goes reaches this surface and reflects back. When that happens, these also form these standing spin wave modes, which can have different half or full wavelengths uh, uh, fitted inside this cavity length. Cavity length means the crystal thickness of the crystal. Now those will again, because they are standing waves and they have also some damping associated with that, that will again draw some energy from your system, and they will show up there as these additional modes. And because by changing angle, effectively you can think that this cavity length is getting modified. So that's why you can see that both the number of the modes that are excited and the spacing of them, those are changing with varying this angle.
Okay. Okay. Thank you, Supriya.
Okay.
Yeah, for the time being, I don't see any additional question. So maybe I can ask one small last question. So it is like a bit naive. So in your
Yeah, yeah.
schematic, let's say we have antiferromagnetic order in CrCl3. So before any transition takes place,
Mhm.
let's say just I increase the temperature a bit from its ground state. So the spins will start to fluctuate, right? Or what is the picture? Means will it fluctuate in plane, out of plane, or how an antiferromagnetic ordered
You are
spin?
saying temperature or
Temperature, I am just saying.
temperature or magnetic field?
Temperature. Just in the schematic, if I try to
Okay, so you're
visualize.
Mhm.
Hmm.
Let me, yeah, let's say this schematic, yeah.
Uh, no, the
Now
next
you're saying
schematic, let's
that,
say. Uh,
okay.
sorry, not this one. Means in just the in the antiferromagnetic schematic where you have the CrCl3 schematic, let's say just before this slide. Uh, no, where you had the CrCl3 thin layer tha. हाँ ये वाला.
Okay,
So
okay.
let's say just I naively want to
Yeah, yeah.
visualize how the spins behave as we increase the temperature
Hmm.
without, let's say, any magnetic field. So will of course start vibrating, right? Or what happens in a typical antiferromagnet?
No, changing temperature will not essentially immediately give vibration, I guess. What will happen is if you increase the temperature up to certain so what the things that will change with increasing temperature are the internal lattice parameters, which are really forming the details of these different modes that are getting excited. So these modes,
Okay.
how they are, so you can see that this exchange term and these are all sitting inside the expression of those modes, right? So I think with increasing temperature, what will happen is because the lattice is getting uh, modified in that, in some sense, because the energy contributions will be different, then what will happen is that will contribute to this mode. And after like above certain, so you can I have not included, but there are some papers which talk about the full um, phase diagram of CrCl3, which has this temperature in one axis and magnetic field
Hmm.
in one axis. So you can see that if you go above certain temperature, then the system can transition to like from being having a magnetic order to non having a not having a magnetic order.
Yeah, that
So
I can
after,
see from
let's say,
this
huh,
experiment.
yeah, so that time what will happen is like, so why these modes are coming into picture in the first place is because there is a magnetic order. So if you go below certain temperature, then the like as you were saying about these fluctuations, so the thermal fluctuations are not enough so that it can disturb the system out of its ordered mode. So when there is no other kind of dissipation or fluctuation, then what will happen is it will be governed by the crystal structure, the symmetry, the presence of the anisotropy, which will determine in which way the spins will get aligned to it in its ground state if there is no other magnetic field, these things. So if you imagine that the temperature is as low as possible, that time system is sitting at that ordered state. Now when you increase the temperature, these fluctuations will obviously come into play, and above certain temperature, it will not be enough to let the system maintain its order, and those moments will basically move around on their own. That's why this that time only you can realize this electron spin resonances, which will be coming out of the individual moments response to the magnetic field.
Okay, so means it's
Moments mean in each of the lattice sites. Yeah.
okay, okay. So means just it's happens like due to means this kind of transitions happens like thermal due to thermal agitations. It just the spin starts to fluctuate, and these transitions happen from antiferromagnetic to ferromagnetic order, or means due to in the temperature.
Not necessarily antiferromagnetic to ferromagnetic, but the most common one you can think, even in case of ferromagnets, let's say, there is a certain temperature above which it becomes paramagnet.
Yeah.
Now when it is paramagnetic, that time also you can see some modes there, which will be very similar to what is shown here at 20 Kelvin. These are called the electron spin resonances. Now here the difference is there is no long range magnetic order in the system, but just due to the fact that there are these, each of the lattice point has spins associated with them. So you can imagine that if you apply any magnetic field, each of those lattice site spins, they will start precessing around the magnetic field. So if you consider overall, you can still get an effect that there is some energy that will be dissipating from your system and will be taken from the channel which you are using to supply the energy to your system, and that will be due to those spins residing on the lattice points, but there is no long range order. Those are called the electron spin resonance.
Okay, okay. Okay, I think there is no more question from anybody. So thanks for agreeing to give this wonderful talk, and I thank all the attendees as well. So let's close the session now, and we meet again in 2 weeks. So thanks everyone,
Okay,
and
thanks a lot.
thank you
Yeah,
Supriya as well.
yeah,
So I
thanks
just
everybody.
end the meeting now.